Hello everyone, my name is Pedro and today we want to take a look at the brain-computer interface Mindmap version 1.3. Compared to last version, it got drastically changed. So yeah, let's take a look at it. The link to this Mindmap is available down into the description and into the channel description. When you click it, you will see yourself here in the introduction section. You can check out the EE section or the extra section, which is some parts about the writing. But if you download the app or even in the web version, you just click the frames and you can see different parts here. We just click on the BCI section and we will automatically be guided here. So I've been working on it for around a year now and it got developed very well. And yeah, starting here, the BCI technology history hierarchy, you can see different part of this technology that is needed. In short, I'm just gonna close it right now, but if you needed a guide on how and on which order you want to read it, just click on the frame and take a look at it. So I'm gonna close this one. Yeah, let's zoom in. So we have the BCI BMI technology. By the way, BMI is another name for that, and other terminology for this technology is provided here. As you can see, it's also called neurotechnology. So yeah, we will take a look at the neuroscience and other fields, but there are other stuff here. We have communities, journals, companies, research groups. One thing that I don't want to consider it here because I'm not an expert in those fields and I cannot comment on that, which is privacy issues and ethical concerns. There are dedicated communities around them, so I leave them for them. If you know any movies in this field, just feel free to recommend me, tweet at me. I've got 2 movies here, it's just really cool. Think that we can do about it. So yeah, so I will make YouTube videos about this, and soon I will add a OneNote page for it to go the details, go into the more details, and I'll put the details in that OneNote. So we have the neuroscience. We want to study what's the brain, and then we have computational neuroscience, which is the modeling of the different part of the brain. Then we have the interfacing. That is the interfacing with the brain, which is invasive, non-invasive, and semi-invasive. Then we have neuromorphic hardwares and bioelectronics. Neuromorphic hardwares are the chipset that just copy the brain-like behavior on circuits and physical devices. We will take a look at them. And then we have neurochips, which they are also called brain sensing chipset. They are the chipset that are connected to the brain invasively, implanted to the brain, if I want to be exact, and get the signal from it. And then we have nanobots, which is just a fantasy right now. And we have hopes for it to make a bright future for us. So yeah, component of this technology is just recording, processing, and generating action. So we get the signal, we process it, and we put some action on it. So before moving on, we have the community section. You can check them out here. I provided some journals here. They're not that complete, but you can find them out. There are dedicated societies around them that you can check them out, and this beautiful picture that you can see channels, podcasts, and other things. I will provide a link to this tweet. You just follow this guy. He or she is a very great person providing this stuff. Beside this, we have review papers. If this part grow larger, I will provide these papers instead of them here, but beside each section for themselves. Alright, so after this we have companies and academic groups, which are really good to follow them and find the cutting edge technology. And if you want to learn about this technology, I highly recommend you to check the academic groups. They are really good. They provide so many good stuff with them, and some section of this Mindmap which will get really technical. I just provide information from these groups. All right, let's go at the top. Starting from the neuroscience, one sentence that really fascinates me is this one. Neuroscience today is like chemistry before periodic table. People knew about elements and components but lacked a systematic theory or classified their knowledge. Even though we know a lot about the brain so far, we know different parts, but we still don't know a lot about different parts, about how they are working. So we have the brain here, and we want to add another layer to it, which we call it as brain computer interface. It's a picture from a book. I will provide the reference to it later. And we have other part of the brain. There are a lot of information about the brain. I provided the link to some of their course. I highly recommend you to start from the crash course anatomy and then go to the edX and Khan Academy. Yeah, and you can see an online book for that, which is really good. I don't want to get too deep on this part because it's a really sophisticated field. We just want to know the main parts that we need to know. And if someone needs to work, for example, if someone needs to design a circuit about neuron, astrocyte neuron, they can just study that specific part for their project. So after that, we have computational neuroscience. For computational neuroscience, we have machine learning for BCI and spiking neural networks and cloud computing. Cloud computing, I think it should not be here, and it should be in the data science section, but I just provide it here. If you have any comment on that, just leave them down to the comment section. So if you want to know about the consciousness, there are two people that you need to follow. There are two videos. First click on this one, watch this video, and then click on the other one. They provide lots of good information about you. There are some good books for this section. I will provide them here, and some good YouTube channels and online courses. So yeah, what people do in this field, they mainly work on the spiking neural networks, which is the third generation of neural networks. I have provided some really brief information in the data science section. It is not completed yet, but in addition to these section, I will provide them here. So yeah, so they use neuron models, and there are different kind of neuron models, and then when they do use those models, they have different topologies, they have different coding based on how those neurons talk to each other. All known neurons talk to each other with the spikes. I will not provide any other further information about these, but I just have the classification here. If I want to provide the extra details, I actually have a PowerPoint presentation, really long PowerPoint presentation, and I provide those more technical information also in that PowerPoint, which I will provide a link to that if I make the video about that. Okay, then we have interfacing section. If you want to just know anything about this section, I highly recommend you to check the BCI guys. They have a really cool introductory course about that. But I've summarized some of the main section to what they are talking about. Not all of it, it's just some of it. And yeah, so in the interfacing part, there are two main rules. One is that brain cannot sense these sensors if their size is smaller than a specific amount. All right, I forgot that amount, but yeah, we have that rule. And every 7 years, these the number of simultaneously recorded neurons has been doubling approximately every 7 years. And there's a reference to that. There's a website that is tracking the size of these electrodes. Alright, there are two books I provided them here. They are really related to the CMOS technology, because after they design it, they attach it to the circuits. Alright, so let's take a look at the type of neurotechs. We have non-invasive, which the most famous of one of them is EEG and fMRI. We have semi-invasive, and we have invasive. We have other types, which is called biocompatible, and a researcher is working on it. I've provided some links to that on the interfacing BCI section on my YouTube channel. You can check it out. They're really cool. And we have also this one from Thomas Oxley. I don't know what category this one can be among them, but their goal is to reach the 100% efficacy. So yeah, if you want to know about these two persons, just search their name and you will see lots of good videos about them. So we have invasive, and for invasive we can implant those electrodes to the brain, which is called central nervous system, brain and the spinal cord, and peripheral nervous system, which is the peripheral around this part. Alright, so for the central nervous system we have different electrodes, and peripheral nervous system we have also different. They have advantages and disadvantages over each other, but the best one of them is just EEG. It has several electrodes on the brain. It is low risk, low cost, high speed, and easy to use. It has some advantages over fMRI. One of them just better in the spatial resolution. You can see here spatial resolution, which means you can see better. And yeah, and oh, by the way, this figure, the next figure is a bit harsh. If you don't want to look at it, just don't. You have FNIR and ECOG, and they are about semi-invasive. They have better signal to noise ratio, which means they get less noise. But if you want to get the best possible signal accuracy, we can use the fully invasive ones, which has the best one, but they are super risky and expensive, and you can see two of them here beside each other. Alright, this was the interfacing section, and there's a picture here. I provided the link to that figure and its article. It's a mouse, it's a rat here, and you can see its brain and a different part of it, and the device that is connected to this. We have different type of these circuits. We will take a look at them later on. But basically what it do is just get the signal, go through the low noise amplitude, and then go to the analog to digital converter, and then we can see the signal. That's all these circuits want to do for us. It has a cable, but there are some type of it that can have an RF circuit part, which just transmit the signal wirelessly. So we can see different parts here. If you want to read it, just click on this and you can see explanation for different figure, or you can just click on this and it will expand near this figure. Let's take a look at it. This is really cool. This is ECOG, and the figure G is just ECOG in a higher accuracy version, in a zoomed in. They use the MEMS technology, and this technology is really good for stimulation. So we have these sensors. They can be non-invasive, semi-invasive, or invasive, or biocompatible. They can either just stimulate the brain, or they can just read the signal from the brain, or they can read it and stimulate the brain. So definitely, if you want to stimulate the brain, we should use the invasive methods. Alright, next part, which is bioelectronic and neuromorphic hardwares. I've invested more time on the neuromorphic hardwares, not the bioelectronics, but I have some good plans on that. I've got some good reference for that. For the neuromorphic circuits, what are they? They are just a bunch of circuits made with CMOS technology or physically that can mimic the behavior of the brain. So if we want to use the CMOS technology, we can go either digital or analog or mixed signal. Alright, for the digital version we have TPUs and FPGA, which is they are also called neural FPGA, NPUs, and for the analog part we have neuromorphic and cytomorphic. So and all they want to do, they want to behave, they want to simulate a memory store behavior. And as you can see here, the motivation behind this is to have the memory in the circuit instead of have them separated from each other, inspired from the neurons which synaptic connection between presynaptic neuron and postsynaptic neuron is just they behave like a memory for our brain and our processors. So you have this roadmap here, and it is predicted in the next 10 years the 3D integration gonna do a lot of work for us. It's currently I know that the Samsung made a 3D memory up to 1 terabyte on the chip. I think it was 1 terabyte, or maybe it's next year. But yeah, it's been developing really well for these years. After we design these chips and other chips and the Neurochips, which I will talk about in the next section, we can connect these circuits to the neurons and get data from the neurons. So there's also a paper for this one, you can check that out. So, and also for this part, most of the stuff that should be done related to the bioelectronics, which I haven't spent a lot of time on this part, but I've provided a link to a very good book, you can check it out. So and yeah, so this was the analog part. For the digital part, I provided a link to a video that you can check it out, and it also has a paper version. But basically what they do is they model the neurons and they model the connection with digital circuits and digital gates. Yeah, okay, let's do a quick summary. So we studied the brain, we know the different parts. We have neuron and computational neuroscience to model different models for us and make some algorithm for us. They are called sparky neural networks and neuromorphic computing. We run these models on the neuromorphic hardware, alright? Because if we run them on normal hardwares, it's just useless. We better not do it at all. And we have the interfacing methods and different methods for that. Alright, now let's take a look at the neurochips. Now we know what to do. Now let's see how we can get these signals from the brain. So these chipsets, in order for them to work really well in the body parts, they need to be low powered, extremely low powered. They should not generate lots of thermal energy, because they hit the tissue, and if they hit the tissue, just damage the tissue. I have different type of sensing the signal from the brain, but I would like to classify them in these 4 manners. First, monitoring. They either monitor the signal constantly, like this. You can see they can monitor everything that they can see, or they just monitor it from the spikes. Let's see a circuit here, right here. See, they just get the spike, and for the noise part, they just get nothing. So the decoding will be happening in the electrode array that we are attached to the body, like this one. So this is 2 category. The other 2 category is these closed loop and feed forward. For what I know, I think all of them are called closed loop, but I'd like to call some of them feed forward, because it just get signal from the brain and stimulate the brain. So let's take a look at the closed loop. Conventional closed loop, which is like this. It gets the signal from the brain, process it, and give it to a processing arm, or it can get the signal from the brain and give it to the hand. If the spinal cord has problem, but the hand is all right and the brain is all right, only the connection between the brain and the hand, the hand from that guy is just, they are all right. Okay, we have two circuits, one in the hand, one in the brain, and these two just stimulate the signal from the brain to the hand. All right, so we have these kind of neurochips. We have another neurochips which is used to stimulate the brain itself, so it should has a neuromorphic part or a digital part for that. So for example, look at the Parkinson disease. The problem is from the brain, so we get the signal from the brain. We just go through a low noise amplitude. Then it goes through an analog to digital converter. Then we have the digital data. We do the digital processing. Then we have a digital to analog converter and an output current driver, which stimulate the brain. All right. So, and yeah, we have also more information from other universities. These are the provided information from some of the research groups. I'm monitoring most of them, but I've provided a link to some of them. I will provide more information about them in the future, but yeah, I think that's it. If you have anything to add to this mind map, definitely let me know. Definitely recommend me your movies that you're interested in. And for the neurochip part, we're doing analog, mixed signal, and digital design, which I've named them here. If you want to know more about them, I have the IC designing section in this part. It is still under development, but I've provided lots of good stuff in the analog part. And basically, if you need to learn them, you just need to find some good online courses about them. I provided several links to some really good online courses here. And if you want to learn the computational neuroscience part, you always need to know about the data science part. So here's the data science part. I'm not an expert in neuroscience and interfacing, so we have the computational neuroscience, data science, and the Neurochip. Alright, so I will make a PowerPoint version of this mind map. I've already made a short version of it, which I explained everything in 10 minutes. I will make another one in a bit longer and provide all this information in a PowerPoint format that you can watch them. The link to them will be available at the end of this video if they are available online. And yeah, with that being said, I would be happy if I see you connect with me in all my social media. Talk to me, chat with me if you want to work on this. I'm happy to develop it. Don't forget to share it with your friend and stay safe. See you soon.